morning, everyone. I hope you all had a fantastic night's sleep. It's warmer in here, so I think we're all feeling much better. Welcome back for day 2. I do have an announcement to make. We have been made aware late last night that one of our participants came down with COVID. So I do want to let you know to please take care of yourself. Everybody that was in close proximity to our participant has been notified one-on-one already, so they have been notified. If you have not been notified, you were not in close contact with this person, please take care of yourself. We have masks at the front desk. We can get more if you need. If you need anything else, please let us know and we can help you to take care of yourself. So, and as we get information, Kate will share information with me, and I will let you know as much as I know when we do know. So, apologies for that, people. It happens. CDC said we can carry on with our lives and just mask and carry on. So that's what we're going to do. And I'm also going to say very thanks to Mike Little for taking the chair position this morning because Ankush is still stuck in India. So thanks for stepping in, Mike.
Okay, so I'm going to apologize in advance. I know you're not supposed to do this, but I'm going to anyway, for every time that I mispronounce somebody's name. So just stand by. It'll be consider it entertaining, and it might turn into a drinking game. That is, you drink when I actually pronounce the name correctly. So anyway, so we're going to start this morning for about 20 minutes to talk about the previous day's working group sessions. And so, Gavin, are you here? Oh, okay. So if you come up and sort of give us about 5 minutes of that, of what went on.
5 minutes is a little more than I'm actually going to need, but in Sun Climate, what we're looking at is making things a lot easier for people, researchers particularly, to access a lot of the solar data for climate purposes. This is a cross-disciplinary enough field, like I was showing yesterday, that people who are working on climate don't want to have to know all the details in the nitty-gritty of solar irradiance or sunspots, but they would like relatively easy access, seamless access to the data. And using a model, the kind of NASA VITA model of open source simplicity for being able to get to data is a role model that we want to follow or build on. That one's much broader. The analogy we had was going after just solar aspects. We're killing flies with a sledgehammer, but the neat thing about that approach is it's very expandable. We're looking at this as kind of heliophysics, getting solar more into climate, but it needs to be broader than that. We need more than just solar aspects. We're eventually going to need but by the way, the VITA is going after greenhouse gases, which is a major part of climate. We would like to add in solar to that, and we can do that through heliophysics. But ultimately, we need a lot more for climate. We need aerosols. We need oscillations, normal weather patterns on the Earth. We need to get a lot more in this. So solar is kind of our stepping stone to get things expanded a bit. But we would like to head that direction with a proposal through heliophysics, building on the VITA model to start incorporating solar. So that's kind of the gist of where we're going and starting to put together a little proposal to that effect. That's probably it for our group for now.
For now, yes. Thank you very much. Yes, sir. Okay, so you're going to do the space weather. Exoplanets, okay. Give me just a second. Let me do the space weather first. So who's speaking for space weather? Okay. Oh, yeah, of course. Let me help.
Hello, everyone. So yesterday, our group talked about open science methods in space weather. And so we started with talking about the existing methods, groups, communities that exist that are doing citizen science, and whether it's in form of websites or open source data sets. And then we talked about what are the limitations that exist if it's reaching all the people all over the world. And if, let's say, a website is there, but it's not user-friendly. So we walked through all those issues, and we came up with a few approaches. So one of the approach we talked about was developing a website where people can upload their data, but then, how to make sure that it works for everyone. So we discussed about those things, and not just about the 3D interactive maps. We also discussed other ideas such as what about the use of social media, or what about the use of TV channels, and about sandbox approaches where people are using or developing 3D tangible models and doing that open science. And the other thing that we talked about was emerging technologies such as AR, VR approaches. And so not just talking about the scientist or the general public, but also defining who are we designing it for, who the general public is. Are we talking about the students here? Are we talking about collaborations where us as scientists can collaborate with computer scientists or the coders, and ways to reach them? So it was all in this brainstorming design phase, and now we are thinking of putting together a proposal of how we can do open science in the space weather domain. Thank you.
Here, let me get it. Height helps. I wondered if it sat there long enough, we'd have a little bonfire. So, you want to, exoplanets is next?
Hello, everybody. My name is Vladimir Arpetian from NASA Goddard Space Flight Center and American University, and I had the privilege to work with the 6 really great team members, the scientists that basically cover diverse fields that can be directly applied to understand exoplanetary environments, including Mang Jin, Shudong Sun, Ankur Bhaskar, Lisa Winter, Mei Yun Lin, and Caitlin Goff. So we have diverse experiences, the diverse views. The one way that we want to start and address this question is that we're living, in this revolutionary era when these over 5,500 exoplanets have been discovered, and we're moving from the era of discovery of exoplanets to the atmospheric characterization. That's where the heliophysics tools come into place. And so of course, the one obvious way to address those issues and to make a sizable contribution with the group will be to move from our sun to solar-type stars, because we understand that the sun is the best star we understand and the best star we can model. So therefore, we, even though we have over 3/4 of the M-dwarf stars, they're pretty crazy worlds, we have plenty of stars. 10% of the old stars in our galaxy are solar-type stars, and might be we can start with the obvious cases of exoplanetary systems that host planet-hosting stars and exoplanets around them. So therefore, we identify the three major topics that we're going to work in the open science. It first to work with the existing catalogs to identify the young solar analogs. So we already have some cases, even though we have so many, tens of thousands of stars, 150,000 stars observed by Kepler. We only have a handful number of solar-type stars that can be, they're close by, that can be observed by the, Hubble Space Telescopes and XMM and other missions for the characterization of their ionizing radiation. As we understand that ionizing radiation environments are very important to understand the climate, habitability, and just atmospheric environments of exoplanets. So basically the second the item will be the data to develop the data-constrained MHD models of X-ray and extreme UV emission, the wind, and the integralization of superflares and coronal mass ejections, the obvious, the high-impact sources of atmospheric evolution. And then the third one is and of course identifying the models that we're using and describing these models and identifying the limitations of those models. And the third item is atmospheric escape models that we currently have in place that been already applied to understand that the escape of oxygen and nitrogen from our Earth during solar flares, but also to enhance them to the exoplanetary environments. And the last topic will be to eventually apply all those tools and atmospheric chemistry tools, the interaction of SCPs with the exoplanetary atmospheres, eventually to apply those tools in order to identify what kind of signatures, high impact signatures, high signal to noise signatures we can find for this upcoming observations with JWST, because our final goal is to develop the predictive science. And so looks like that our goal will be to write a white paper to address all those issues and to see that where we are at this point. Thank you very much.
So the next talk will be by Jennifer Gannon, who's the Vice President of R&D at Computational Physics. And I have to say, the title of the company is one of my favorite titles in the world. I mean, just think about it. Computational physics. Is that?
It sounds like a grad course.
It does, yeah. Thank you very much.
And you got my name right.
Well,
So,
I'll give it another shot.
yeah, okay. I'm bringing my coffee because it's a little cold up here. I think it's a little warmer today. That's kind of climate change I like. So I'm going to talk about data today. I got my slides up. I never know how to use these things. Does this have a back button?
The red one is red.
The red one's a back button? Okay, green forward, red back. So I'm going to talk about data today, which is, something that is extremely powerful in science. One of the foundations of most of what we do in space weather. And I'm going to specifically focus on ground-based data. So I'm going to start off by saying something that you may not agree with, which is that ground-based data has kind of become maybe a little undervalued. A little less popular, maybe a little not as cool as some of the space-based assets, and that's a little bit of a shame because there's so much history in the ground-based data, and so much of the ground-based data goes to support a lot of space weather indices and understanding and modeling, and it's just critical to what we know about space weather impacts. The positive way to put that maybe is that there's so much exciting space-based data that we're just kind of a smaller part of the toolbox now. But as that shift has happened, a lot of that ground-based data is moving to the commercial sector, to industry. And that comes with a lot of opportunity, a lot of new sources of data, and some complications for open data. So I'm going to talk about that a little bit. I'm going to use a power grid example from a storm from 2021, a G3. And the analysis of this event would not have been possible without a new source of open data from the power industry, which is a database of GIC information that's been really, really useful. So first of all, in this shift of a lot of ground-based data going to the commercial sector, or the use of a lot more commercial sector data, one thing hasn't changed. We tend to focus on extreme events, the big grid-killing, end of the world kind of events, because that's the stuff that we want to avoid. And when we're talking about space weather and space weather impacts, that sort of makes sense. There's a lot of really, really good science in the moderate and small events, and that science can lead to better understanding of the extreme events. So as we've moved to industry, that really hasn't changed. The power industry also is looking out for these large events, and they're trying to measure for large events. So most of this database that I'll talk about is really focused around storms. We don't have a lot of quiet time data. It's storms that are KP7 or higher, G3 or higher. Oops, got a movie in there. So the event I'm going to talk about is the May 12th to 13th, 2021 geomagnetic storm. It's a little bit of a boring event. I mean, it was a nice event, but it wasn't exciting. It didn't bring down anything in the power grid. No one died. It was kind of a typical normal G3. It was super exciting to watch because it was one of the first G3s coming up into Solar Max, and we're like, yay, we're getting some activity. But the event itself wasn't that exciting for the power grid. However, we had this new wealth of data in the NERC ERO database. So I'll get into a little bit of the history of how that database came to be, but we had a lot of GIC measurements from the power grid that we'd never had before that we could start to look at about this time period. And we picked out this event, and we looked at it, and we saw this time series. So this is measured current in a substation in a transformer just outside of the DC area. So measured GIC data, not modeled, not magnetic field, measured currents going through the power system. And there's a couple interesting features of this storm. So first of all, there's a peak of 30 amps per phase. Again, not catastrophic. The power utilities don't really get concerned until it gets up to about 75 amps per phase. So this is maybe half the size of what they'd really be looking for. And it's followed by this 3 to 4 hour period of heightened GIC. It's not at the same level, but extended periods of GIC like that can cause different kinds of issues for the power utility. So that really caught our attention. What could cause this kind of extended GIC? Could it be bigger? If it could be bigger, that could be really bad for the power utilities. And this is right outside of the DC area where we really weren't expecting it. So it was a weird event. And because we had all of this open data in this GIC database, at this place in Fredericksburg, this one substation, I think there were 20 or 30 measured storms they've been measuring for quite a while, and just opened this database up. We looked at the history of other G3, G2 storms, and this storm was just different. It was so much larger than anything else that had been measured at Fredericksburg. So again, it was a clue that something was different here. It's something that we needed to understand, because if you could create these kind of conditions during a moderate event, what would it take to create these conditions during a larger event when it would really matter? So these are some other measured GICs at that location outside of DC. Okay, so let's get into a little bit of the history of the GIC database. So for those of you not really familiar with the GIC history, there is, I'm sure everybody's heard of the 1989 event, which caused such problems for the Quebec power system. There was some cascading power failure. At the time, nobody attributed that to space weather. They actually blamed the power utility. This whole GIC thing kind of began around that time when we realized there could be power impacts. It took about 10 years after that for it to become really well understood that this was a space weather effect on the ground. Because of that, the government, FERC, the Federal Energy Regulatory Commission, directed NERC, which is a consortium of power utilities. It's a corporation that's made up of power utilities, working in the interest of power utilities, to assess the needs for mitigation for space weather and really to kind of self-regulate, to put together their own set of rules and mitigation procedures to prepare for space weather, and that's called TPL7. So that's a federal regulation that directed the power utilities. So as a part of TPL7, the power utilities had to do a bunch of things. They had to assess whether they were vulnerable using a set of really kind of simple criteria, and if they were vulnerable, move on to more stringent criteria. But it also directed them to measure, to take measurements of the magnetic field or to use measurements of the magnetic field. They didn't have to do it themselves, but they had to have measurements of the local magnetic field, which drives the GIC, and they had to have measurements of the GIC themselves. That's where the regulation stopped. It just said measure data, full stop. Didn't say how much, didn't say when, didn't say what to do. And so it really could have just kind of died there. And it didn't. So recently, maybe in the past 5 or 6 years, there was this, I forget what they call it. It was a data request. So NERC put together this data request to the power utilities and said, okay, you've been measuring this data, and power utilities are concerned about GIC, so they put out more than just 1 or 2 monitors. They put out hundreds of monitors across the U.S. I think for each storm now, there's probably 700 monitors that are reported for each one of these storms. And they said, please release this data publicly. And this had been a long battle, a long kind of, at some point, uncomfortable conversation about getting this data. GIC data for a long time was really, really hard to get unless you could go work with a power utility and sign an NDA, and they trusted you, and only you could use it, and you absolutely could not publish it. This was a big shift. I still don't completely understand why they agreed. I mean, what shifted in the culture or in the partnerships between the researchers and the utilities? What shifted that made them take this leap of faith to open up their data? Because this is voluntary. It is a voluntary action on the part of the power utilities. Well, it's been, it's a vulnerability. It's a measurement of vulnerability in their system, So they were concerned that it would point out where they were weak. They were concerned that it would bring more regulations down on their head. They felt they could handle it internally. They didn't want the regulation to come in and cost them billions of dollars. So, but they'd also seen, a decade of good science coming out that really helped them, and it was science that they didn't have time to do. So I think that's probably part of why they released that data, and it's been a wealth of information. And we're just starting to dig into it. It's all out there. You should all go look at it. If you're interested in GICs, you can log in and see. Okay, so that data is made available. So for those of you who are not GIC people, what we usually look at when we're looking at the drivers of GICs, or you get a big CME. Those are what causes the biggest GICs in the power grid. The CME impacts the earth. You get a big reconfiguration of fields. You get current systems enhanced, all the stuff that you guys already know about. And that drives a varying magnetic field on the ground. So like much of space weather, the magnetic field is the driver of GICs. The magnetic field then induces electric field at the surface, and that electric field induces a current in anything that's a long line. So the magnetic field is really important. So the next source of data I'm going to talk about is magnetic field data. Magnetic field data is critical to understanding GICs. And you have to have it kind of locally. So if I go back to this previous plot, it's a reconfiguration of fields, but it's a reconfiguration of fields. It's a change of a dBdt in the presence of a non-uniform conductor, which is the Earth, and I'll get into that in a little bit too. So it's a complicated E. It's not just a B in a vacuum producing a perpendicular E on the surface of the Earth. It's a lot more complicated than that in space and in orientation. So you need a lot of magnetic field data. So this data, this is a magnetic field magnetometer network run by CPI, the company that I work for. That's been funded by NSF for about 5 years. We're extremely grateful to NSF for continuing to support this network. We work closely with the power utilities, and they regularly use this data and love using this data and love having the local measurement of the magnetic field. So we had magnetic field data available. Because it's funded by NSF, it's publicly available. And we've been trying to make sure that it can get out to as many people as possible as well. So we have this, and we could see from the magnetic field that there was a remarkably uniform variation in magnetic field across the U.S. So these are a bunch of different locations in the U.S., from the West Coast to the East Coast. During a GIC event, you often see the magnetic fields kind of chaotic, particularly in orientation, which causes some of that complexity, some of that local complexity. But we saw that something that was really surprisingly uniform across the U.S. from this measured data. Okay, so I said the Earth is a non-uniform conductor. Faraday's law, changing B induces an E. But it's in the presence of the Earth, of this non-uniform conductor, which is the Earth. So that has a couple of different effects on the electric field. Very sensitive to frequency. So because the Earth has different conductive layers in the mantle and the core and the crust, which have different properties, the electric field that is induced at the surface is a function of how deep the magnetic field can penetrate. So that skin depth of the magnetic field means that it can go to different depths into the Earth, which means you get a different frequency content interacting with a different layer of the Earth. So we've got a frequency content dependence on the magnetic field and on the GIC hazard. So you got to have highly resolved magnetic field data. You have to have 1 second magnetic field data to really get the full GIC response. But it's a little bit more complicated than that. There's also non-uniformities in latitude and longitude in space. So look out the mountain, out the window. There's a bunch of mountains out there. That's a big conductivity structure that's different than the plains. So it's different laterally as well. So it's not just varying with frequency because of that depth. It's also varying by location. And the more complicated the conductivity structures, the more complicated that Jackson E&M problem becomes an induction of E. So you get E pointing in a bunch of different complicated directions. So you get a lot of local complexity. Luckily, again, we have lots and lots and lots of data. This is from the University of Oregon EarthScope project, again, NSF funded. So NSF funded this project to march across the US, measure conductivity on a 70-kilometer grid. I forget what the original goal of this project was. It wasn't GIC specific, but wow, it became really useful to GICs because it's really going out and it's mapping how the local hazard changes in this 70-kilometer grid, and it's giving us a bunch of data to do this induction and do this calculation. So again, NSF funded through a university, so this is not private sector, completely open data through IRIS. Okay, so from this MT data, we can know which parts of the US have the highest GIC hazard. It's upper Minnesota, which has a really high area of GIC. And this plot, it's not color-coded, it's kind of like random color-coded, unfortunately. The numbers that you probably can't read are the relative hazard. So it's a number relative to the hazard in Quebec during 1989, which is maybe a little bit arbitrary, but since it all started in Quebec in 1989, that's our reference. So a higher number is higher hazard. So upper Minnesota has a 2.7, which is fairly high. I mean, you can see the effects in some of the GIC data coming from there. And in Maine, Maine really has a unique situation in terms of GIC in the continental U.S. because it's got a completely different geological structure. It's kind of been, I'm not a geologist, but it was basically glued onto the U.S. through some of the processes over time, and it's made of a different kind of material, and it also has a pretty strong coast effect there. So you get a difference in conductivity between the earth and the sharp drop off into the water. So Maine has a very high response. I think it's, 3.5 there, 3.3, and then all along the Appalachian Range, you get like a 4.4 and a 2.7. So think DC to New York. DC to New York is that high hazard corridor. And there's a bunch of regions in the middle, like here, where we don't have that much of a response. If it's flat and open and sandy, it tends to be a little bit less hazardous for GICs. Okay. Yeah, well, it's the lakes are not. The lakes don't contribute as much because they are freshwater, yeah, they're freshwater. But there's also there, and again, I can't remember what the name of it is. There's that blade of material that comes down from the Canadian Shield. That it's the same reason that Quebec has the high hazard. So does Upper Minnesota. They've got a blob of material, deep earth conductivity structure there that makes it hard for them. And it's very isolated right around that Upper Minnesota area. And there's some really interesting transmission lines going through that region as well. So it's a good region to study. So from this data, really important data. We know there are areas that are particularly complex. I mentioned this New York to DC and Maine and Minnesota. So each location, the more complex it is, the electric field isn't going to point the direction you think it is. If B is primarily north-south, but it's waving all over the place during a storm, in these complex regions, the E may not even vary in orientation at all. It may be fixed just because of the nature of that conductivity structure. It has a preferential orientation, and sometimes that preferential orientation is in a really disadvantageous location with relation to a power line. So you get an E like this and a power line like this, that's maximum GIC. Sometimes it works out really well. The E is like this, the power line's like this, they rarely see anything. That's kind of the case in this DC site that I'm talking about. That's why you rarely get the GICs in that location, is that E is typically perpendicular. It typically doesn't really align with the power grid structure around there. So we got a lot of complexities, and the data really helps us dig into what this is. Okay, now we get into the real complexity. So you've got E pointing all sorts of directions. You've got this all changing with time. You've got the conductivity response creating a lot of this variational hazard from place to place. The power system is an incredibly complex machine. I did not understand this as a magnetospheric scientist going into the GIC world. This is an incredibly, amazingly balanced, just complex miracle of human creation. And the fact that so many people get together and keep this thing going and keep it, keep the power on in such a consistent way is really, it's really impressive. Because the power grid, you've got all these different lines going in different orientations. Each interconnect has to oscillate completely in phase. They've got to balance the generation, the input, and the output. So people turn it on all their ACs at once, and it's just an incredibly complex process. So when you're trying to look at GIC hazard, you're taking something that's already kind of physically complex, that electric field, and mapping it to something that is structurally complex, which is this highly interconnected power system. Not only that, there are a lot of parameters within the power system that affect how the GICs can get induced in the lines. So the substation, how is it grounded? Was there rainwater that day that changes the grounding? How long ago was that substation put in? Because that grounding is going to corrode over time, and that makes a huge, huge difference. What's the conductivity, the resistivity of that long transmission line? What are the voltages of the step-up and step-down transformers? Where do those lines go? You know, we tend to map them as straight lines between points because that's easy, and we don't have the rest of the information, but they don't, you know? So what if one of those lines goes around a mountain and through an area of high electric field and not necessarily, you know, over the mountain where like that straight line distance seemed to imply? It's very complex. So there's a lot of data and information in here. This is all owned by the power utilities. So there's a lot they do with these models. You know, it's a lot more than GICs. GIC is a small add-on to this. You know, they use this to balance load, to model their systems, to see, you know, how they should respond to all sorts of different kinds of changing inputs. And there's a lot of really proprietary and sensitive information in there that's also needed for the GIC calculation. So this is where some of the GIC data becomes more difficult to access, but it's also where a lot of the really good science is being done, you know, because you want to connect the driver to the actual impact. And if you're going to really use this GIC data and this GIC, this availability through the NERC database, it's pretty important to make sure you're using a realistic grid, which means working with a power utility or working with a grid partner. Doesn't mean you can't do anything with the GIC data on its own. There's a lot of good science that's being done without using the full grid model, but this is really the way to get to a true estimate of the impacts. Okay, so what do the power utilities do with all this? They do what's called a GIC model validation assessment, and it's assessment of their models and of the geophysical models. So they've been told measure the magnetic field in GIC. They ostensibly have that. They take that electric field, excuse me. They take the magnetic field and they calculate the electric field using a conductivity model, starting with something really simple and then getting more complex, just like we've described this whole process. They take their system model, they apply this electric field to their system model, and they estimate GIC in their critical nodes. Okay, they've estimated the GIC, they've measured the GIC, they compare it to see how close they are. And you should get something like this. The red line is measured, and the blue line is modeled. It's modeled using one of the more of the simplistic conductivity models and a really, really local magnetometer. So this is one of the upstate New York, the NSF-funded MagStar mags. And this was done in collaboration with EPRI. Now, it never, ever, ever looks like this to begin with. It's never this close when you put it in there, and it's orders of magnitude off, because you know, this is a pretty young field. You know, we're just starting to understand how to really get from E to specific GICs. We had one that was incredibly frustrating, that we put it in, it came out perfect, it was gorgeous, and we were so excited, and then the power utility came back to us and said, oh, wait, we forgot. That was during the storm, and this other line over here that we didn't tell you about was completely down. You got to take it out of your model. Took it out of the model. Of course, completely didn't matter. Completely messed up our results. We were very upset. But it's tweaking things like that, and that's why it's a model validation. They go back and they make sure their models are right. Go back and make sure their inputs are right. Are they using a magnetic field that's local enough? Are they using conductivity models that are complex enough to represent their region? And they do these model validation assessments to make sure they have the tools to model the extreme events. So, okay, we trust our tools. Now let's apply an extreme scenario and see what fails. But if the tools don't work, that scenario is not believable. So that's what the model validation assessment is for. So this event has also been part of a model validation assessment. I don't have that output to show you, but we learned a lot just from the GIC data. So there was a bunch of surprises from that storm. I mentioned that 3 to 4 hour elevation of GIC data. We combed the database. We really didn't see many other events that were like that. So this is not a common kind of occurrence. And it was larger than expected in the DC area. So, and like I showed you, it's kind of uncommonly large. So this was a weird event. What else can we see from this data that might be unusual? What? I'm down to 5? Okay, thank you. I'll move on quickly then. So we dug through the data. I think for this one in 2021, so there were maybe 500 reported GIC sites. And we started seeing the same profile at a bunch of different places, you know, Fredericksburg, or right near Fredericksburg, DC, Pennsylvania, all of these places where we hadn't really seen elevated GICs before. And the profile was almost identical at all of these locations from about Kansas all the way to where we had data in New Jersey, which is, again, really weird. We haven't had this amount of data to look through before, but that's really, really weird. Here's the state of Virginia. The model validation is shown in the circles. So big circles are big modeled GICs. The plots are all data from that database. A couple more examples. Here's New York. Same thing. New York wasn't as high as Virginia during the storm. Again, weird. Maine wasn't as high as the DC, Virginia area. Again, very, very strange. That should be kind of the highest response area, although they did have some pretty big GICs. So what happened? We don't know yet. This is an ongoing work with NASA and University of Colorado, with Dolores Knipp. For some reason, mid-latitudes were unshielded during the storm. It could have been because there was a 1-2 punch from a double CME that came in. So the second CME was interacting with the first, or the first CME preconditioned the magnetosphere to make the mid-latitudes more susceptible to these varying B, or to change the characteristics of the B on the ground. It's ongoing work. So kind of to recap, just a couple closing slides here. All of this work is done from ground-based data. Magnetic field data that's NSF funded, MT data that's NSF funded, GIC data which is utility owned, and it's just it's a blessing that they are making that data available to us. They did not have to, and they did, and it's just spurred a whole bunch of research. And then the power grid models, which are also utility owned and very sensitive. So the complexities are here, you know, often come down to a couple different things. Would I have like 2 minutes? I got to speed up. Exactly 2 minutes. Okay, so where is the funding for the data coming from? The first two are NSF funded, therefore publicly available. That makes open data easy. The GIC data is not publicly funded. The GIC data was funded by the utilities to handle a specific problem, which was the regulation and to understand their vulnerabilities. And it takes time and money and effort to make that data public. So it poses a complication to making some of this data public, and also a little bit of fear of exposing vulnerabilities. Data acquisition and management just takes a lot of time and knowledge. One thing I didn't mention about this GIC data is of the 500 sites that are available, 25% of them are really good data. They're all done by EPRI because they are data people. They know how to put in these GIC monitors. 50% of them are probably usable. The other 50% of them, flat lines, noise, you know, it takes time and experience and a lot of effort to really make data of a quality that can be used. And that's an ongoing effort within the power utilities. And there's some very real sensitivities associated with this data that we discussed. So to wrap up, and this will be my last slide, there are benefits to open data. I mean, it's clear that making this data open has spurred a lot of research and a lot of what I think is really interesting, moderate storm that can inform extreme storms. But that data sharing, making that data open requires more than just, you know, a desire for it to be open. It requires trust. It requires collaboration. It requires really communication, and those are hard things. Those are hard things to accomplish. So every time we're trying to talk with the power utilities, and you know, I would suggest in other cases where you've got some sensitive commercial data sources, you know, we have to ask, how can we make the lives of our end users easier. They have a lot to do. They have a lot to do. You know, they don't have the time to do this just because we like it. You know, so how can we make their lives easier? What can each sector do best to improve efficiency? And most importantly, are we improving that collaboration, that communication, and that trust so that both sides can benefit? And you can make the data open, and you can do all this wonderful science, which will then benefit the end user. So it's a process, is what I'll close with. Thank you very much.
Thanks, Jennifer. We have about 15 minutes, sorry. I'll start it now,
Okay.
for questions. So,
Thank you. It's a whole new area for me to be thinking about. But aside from the geological structure that you've got to work with, it's pretty static. How dynamic is weather on influencing things? That is moisture in the air or uplift or lightning storms nearby? How much does that influence the localized results you get?
We don't know. We haven't gotten there yet. That's a layer of complexity that we're just starting to touch. You know, that groundwater component is huge, particularly with the higher frequency, and the higher frequency affects more than just GIC. It's also, you know, the higher frequency Bs, magnetic field, that can cause power grid problems. So you know, non-natural GMDs. So the groundwater component is huge. Lightning can certainly affect measurements. You know, so you've got the data processing issue. Weather conditions can affect how well those GIC monitors are working, because they're just Hall effect sensors sitting on a line. You know, so you've got corrosion on the line that can certainly affect it, but we don't know. There are some big error bars in each of these steps, and that's one that definitely needs to be approached.
Okay.
Thanks for an interesting presentation. The question is that, what is the time resolution of your measurements, dBdt? Because that basically defines your current, right?
So for the magnetic field?
Yeah, for magnetic field, right.
1 hertz. Yeah, so it's 1 second
hertz.
cadence. You have to have 10-second data to really resolve. About 50% of the electric field comes from the data in between 10 seconds and 1 minute. So there's a lot of 1-minute data sources out there, and you can use them for GIC hazard, but in the really responsive regions, it's that high frequency that really makes a difference.
And this is the highest characteristic frequency for the magnetic field variations?
The highest characteristic, no. So you get low power in that, and lower power in that, so it becomes even harder to resolve.
Okay.
And then there's a dropout actually under about, I think it's about 10 seconds. There's a band. There's really not much power. So 10 second and faster, or 10 second and slower is most important.
Thank you.
So you showed a map of 70-kilometer grid of all the points. What is happening in Texas?
What's happening in Texas?
It's empty.
It's flat. Texas is flat. Have you ever been to Texas? Texas is very flat. Which one? Oh, yeah. So the MT measurements haven't quite. I think they're still finishing up the processing for that part of the U.S. That's kind of a lower hazard area. So they moved north to south and west to east. So they're getting to Texas, and every time we get more MT data, we reprocess it. But it's in most of Texas, other than along the coast. You know, the coast has got some complexities. It should be fairly uniform. So having a few sparse points will well represent the conductivity response there.
Texas is great. It's not connected to
I was just talking about this with somebody. There are 3 parts of the grid in the U.S. So there's the eastern and western interconnect, which are connected by a DC link. So the eastern interconnect has to oscillate in phase, but it doesn't have to oscillate with the western interconnect. They operate differently. Texas is on its own grid, because, you know, it's Texas. Again, I'm from Texas, so I can make fun of Texas. It's by itself. It's also unique in terms of its regulatory response. It's almost completely unregulated, which is why they get some interesting interesting economic effects down there on the grid. But I believe, and maybe somebody in here can correct me if I'm wrong, I believe there is a DC interconnect between the Texas grid and either the east or the west. I don't think it's completely separated, but it operates independently of the other two.
I think it is.
Oh. Yeah.
Putting in a connect to the IOUs because they've been subject to federal regulation,
Ah.
management, and so that's why.
Maybe, yeah, that sounds likely. That sounds likely. But it does operate independently of the other two interconnects.
Thanks for the talk. My question is,
Let's
are
see.
you hoping that NERC releases their data for KP values less than 7?
Yeah.
And I ask that because, when you look at a geomagnetic storm, KP sort of paints everything with a broad brush, right? It's a 3-hour average, and you see these DBDTs fluctuate really quickly, but they're pretty intense during the weaker storms sometimes. So.
Yeah. KP is a horrible index for GIC. It has nothing, it's really not very well correlated with GIC because of the frequency dependence. And GIC is really not well correlated with DBDT either. It's a really good proxy at times, but it's really that spectral content. It's the high frequency versus the low frequency and how it interacts with the conductivity. It would be great to get more data. First, it would be great, and I know NERC is working on this, for them to loop back with the power utilities and help them improve their data collection so that the data that we do have for these events that are happening now is a little bit more usable, so we can get above that 50% threshold. And they're working on it. They're motivated. They're doing it. So.
Excellent talk. You can see from the number of questions. So since kind of the fabric of this meeting is open science, data acquisition and dissemination. I mean, your talk took me back to space. And I'm just thinking, we just recently had an eclipse. I want to give the context. And what we realized that LRO data has created a topography of the moon that is less than 1 meter resolution. And someone told me that we don't have that kind of resolution for our own planet. So given what is needed here and the questions we are being asked, and this is still very important, we know, can we resort to space-based measurements, maybe even from the moon, right? To map this region, whether it is conductivity. There must be ways, right, that we can figure out features. And where are these data available? Because lots of different tools are being utilized now. Since you have decent models, predictions, validation, can we also bring the larger tools of AI/ML and see if we can construct something? That's another way of validation. Excellent talk. And I'm going to pass this on to Simon and to him because we all had questions.
Okay. I'm sorry, I kind of forgot. The question was, can we use space-based data?
Can we think of ways of getting space-based data?
Yeah, and the fluctuations in B on the ground, the DBDT, the B variation on the ground is driven by ionospheric currents. So one of the best metrics for where you're going to get big GIC impacts is where are you in relation to the auroral boundary. If you're sitting right under the auroral electrojet, that's a big DBDT, that's a big GIC. And
Not direct, right? That part we know we're trying to tackle, but ground conductance, for example.
oh, ground conductance from space.
Can we map that?
Yeah.
The other side we are familiar with, and yes, we know what to do. Not all of it is done.
Yeah, they're finishing the U.S. on the ground conductance. I think it's cost effective to do it on the ground. I can't think of a way to do it from space. Doesn't mean there isn't one. Somebody smarter than me could come up with that probably. But it's one of the benefits of the ground-based data is it is cost effective, and they can go and they can move these instruments around as conditions vary and as they need to leave them longer or shorter or retake data or go fix an instrument. So I think it's most countries that I'm aware of are doing it from the ground. But I don't know, interesting question.
Kind of like a sort of
Oh, yeah. Yeah, there's the right answer. Yeah, that's the right answer. That's the correct answer. Satellite-based soil moisture, because we need that metric of soil moisture to get to the next step of accuracy in GIC. Yeah.
So, following on the theme of open science, one of the issues that at least we used to face was getting information on space weather effects out of commercial entities and even out of parts of the government, whether it's for competitive advantage reasons or security reasons. Is that still an issue, or are there ways to deal with that? Or
Yeah, I'm going to go back to that trust and relationship building. I think the reason I like this event so much for this forum is that this data wasn't open for a long time, and it is open now, and it's extremely valuable. It's extremely valuable to everybody, but it really did take a leap of faith from the power utilities that it wouldn't be used against them. And so I think it comes back again to that relationship building and that trust building with the end user and understanding the needs of the end user. And this is a success story. This could be a model for how other industries do it.
Thanks. Once again, excellent talk. You keep hearing that from all of us. I had to jump in. Earlier you said, I don't know why these people open their data.
Yeah.
And that drove me to comment, especially for the younger folks in the room. We owe almost everything good that happens in the field to somebody who had a wild idea and saw it through. In this case, we owe a lot of thanks to Ernie Hildner, who ran the Space Weather Prediction Center for a long time, for really lobbying folks to open this data. People like Bill Wagner and Alan Title from NASA, who opened up the NASA side. The comment really is, if you see something that would be great for everybody, pick up the phone. Make some phone calls, try and build those relationships and make it happen. These things don't just happen, right? You make it happen. And we're right now reaping the fruit of seeds that were planted 20 years ago. So
It didn't happen because there was a federal regulation telling them to. It happened because there was a request, and they trusted the person who made the request. I don't know in the end, who it was that really pushed it, that final step. Like you said, there's a lot of people that have been trying to advocate for it for a long time and done a lot of good for the GIC community and for the power grid community. But yeah, relationships, trust, and pick up the phone and make a friend and try to understand where the power utilities, what their needs are and where they're sitting and what they're thinking.
Over here. Hi, Jen. Question along the same lines. So this situation of trust can be quite fragile. So I wonder if there's some sort of protections that can be put in on the data usage so that these companies aren't faced with this billions of dollars of unfunded regulations. Don't get me started on the unfunded, because that's a problem in itself. But I wonder if there's some sort of protections that can be put in. What would you recommend?
There are, so I think looking at the data request, it was a request. It was optional. That made them feel more secure. Like it was, they were being able to make a choice. They were also allowed to downgrade the location information, which is one of the things they find most sensitive. So the lat and long pair is, they don't have to give the full latitude and longitude. They can give it to 1 decimal place, which is good enough for most of the grid modeling work right now. On some of the grid models, I think there's a lot more that could be done to separate the sensitive information from the stuff that we do just for GICs. The GIC data really, that part of it isn't that sensitive. It's the rest of the grid model that comes along with it. But that takes time and effort. The power utilities, in terms of funding, if it's under a regulatory mandate, they can pass that cost on to the consumer. So they can pay for it if they want to and if they feel that there's a need for it. Again, I think it comes back to building that trust with the end user and understanding what they need versus what we need and making everybody win. Everybody's got to benefit from that large amount of work that it would take to separate the sensitive from the non-sensitive. But I think it's doable. Yeah.
So we have time for one more question. Anybody else want to take a shot?
I have another comment, and it's a more cynical comment, because it has been a very positive interaction here that you have a measure of trust with these companies, and you have an interpersonal relation that makes them give you the data and lets you use it. But I'm thinking of this in terms of more like, PyTorch or TensorFlow, where these big companies, they made these packages, they use them, and then it's made public because they see a lot of potential in the public to actually use these packages, come up with stuff, and then now they can leverage on all of the stuff that's been done by the public for their own benefit. So if you're getting something for free, you are the product.
Yeah.
And you are being brought, basically. So there's something else. I mean, let's face it, I mean, a lot of these companies exist to make profit. They're not here for charity. So I think, I mean, it's nice to say that they trust us, or there's some great brotherhood that's going on, but I would still be very cynical as to, okay, what are the general aims or what are the general requirements from your side that need to be satisfied, let's say not now, but in 20 years or something, which the community will eventually come up with, because once the data is made public, you have innovation coming from everywhere, right? So this is just a thought I wanted to put outside, and maybe have your comments on what you think about this.
Yeah, I think it's a great point, and it gets to what that data sharing can really provide. I mean, the benefits to both sides, spurring the research, which will then help the power utilities. I have an optimistic view that that's why they released the data, that they started to see some of the benefit of the science working for them and making their lives better and showing them where their vulnerabilities were. And so they said, okay, we'll release a little bit more and see where this goes. And hopefully it snowballs and we get a lot of data and they get a lot of benefit and we're all safe. I will say the power utilities, yes, they're corporations, but they're also made of a lot of people. And those people are not there for a profit motive. The people are there to keep the lights on because they love this beautiful machine. I mean, they are engineers that love the power system. So they're not that different from us as researchers. But I think that just that supports this idea that we can all win, and that I hope you're right. I hope we release it, and the benefit they get is from the science that comes out. Yeah, they're not. Hopefully, they don't sell our data like Google, but
Well, thank you very much.
Thank you.
Truly an excellent talk. One last round of applause for Dr. Gannon.
Thanks.